Hi everyone. In the previous video we introduced the concept of energy, and I tried to give you a few different ways to quantify, not really quantify, but categorize energy so that you could better understand it. What we're going to do in this video is introduce you to the concept of entropy, because entropy is going to be really key in our attempt to understand why some chemical transformations occur and why others don't. Here's a couple of buzzwords. If something happens in chemistry, we call that spontaneous. If something doesn't happen in chemistry, we call that non-spontaneous. So we're ultimately going to use the idea of entropy to help us understand why some things in chemistry are spontaneous and other things in chemistry are non-spontaneous. So let's begin by looking at a couple of examples. All right, here's an ice cube. I alluded to ice melting in the previous video. We all know that ice melts. Now, we might need particular conditions to get the ice to melt, but if we get those particular conditions, the melting of ice will be spontaneous. We know it'll happen. What we're going to eventually be able to use entropy to do is we're going to be able to do the thing in science we like to do, and that is we're going to be able to quantify why ice melts. We're going to quantify the extent to which the melting of ice is spontaneous. Or here's another example that I'll sketch out. Think about a ball rolling down a hill. Okay? We all know that when you put a ball at the top of a hill, and if you give it a little bit of a nudge, if you get it to the edge of the hill, we all know that that ball will spontaneously roll down the hill. That would be a spontaneous process. Just like the melting of ice under a particular condition would be spontaneous, a ball rolling down a hill is also spontaneous. But what about the other direction? Let's say that instead of talking about a ball rolling down a hill, we have a ball at the bottom of a hill. And what we're going to do is we're going to transfer some energy to that ball, maybe by trying to heat it up. So that's a little flame under the ball. And if we heat that ball up, what is not going to happen is the ball does not spontaneously roll back up the hill. No matter how hot you get that ball, it's not going to spontaneously roll up the hill. And this begins to get to the issue that entropy is going to help us resolve. How can we quantify the possibility, the probability, in fact, the spontaneity of a ball rolling down the hill versus quantifying the non-spontaneity of a ball not rolling up the hill, no matter how hot you make it? So we need to try to understand why these certain transformations happen and why other transformations don't. This is what entropy is going to help us do. Now, as we describe what entropy eventually is, I want to kind of start by talking about what entropy is not. You're going to hear some words that get associated with entropy. For example, you're going to hear the word random or randomness, or perhaps even disorder. I'm not a big fan of these words being used for entropy. If something is random, then you truly cannot predict what's going to happen. You know, life is filled with random events. There are random accidents, there are random situations, and there really was no way to predict that that particular event was going to happen. But the same is not true with entropy. We will be able to predict what's happening to the entropy of a system as it progresses in time. Entropy also is maybe not best described as using the term disorder. Because again, if something is disordered, it's really hard to quantify. It's really hard to put a number to the state of that disorder. So I want to try to get us to move away from the idea of randomness and disorder. Now, it's true that random events like molecules colliding with one another, it's random whether molecule A collides with molecule B or whether molecule A collides with molecule C. Those are kind of random events, and those random events do contribute to the change in entropy of a system, but the entropy change itself is not random. So let's try to get away from random and disorder. What I want to focus in on when it comes to entropy is that entropy really is a way of describing the number of ways a system can be arranged. And if we can figure out the number of ways a system can be arranged, and we can, then we're going to be able to quantify that system's entropy. Let me give you an example. Let's take, say, a glass of water, okay? We're going to be able to describe a couple of different ways in which that system is arranged. If all the molecules of water are in the one cup of water, that's going to describe one particular arrangement. Now, what I could then do is take the same amount of water and I could distribute it into a whole bunch of smaller containers. And that would sort of increase the number of arrangements that I have available to those water molecules. And if I increase the number of ways I'm arranging a system in physical space, as I'm showing in this example, then I'm increasing the entropy. So there's one way we can change entropy, and that is by changing the physical arrangement of the molecules. Taking all the molecules from one container and dispersing those molecules into multiple containers would have a change on that system's entropy. Another way we can change the entropy of a system, another way we can arrange the system, is we can talk about the way the system is arranged energetically. What if I take this first larger glass of water that I'm talking about, and instead of having it at some room temperature, maybe I go ahead and I heat it up again. All right, so I put it on a Bunsen burner, I put it on the stove, and I heat it up. Now, I'm not changing the physical spatial arrangement of those water molecules. All the water molecules are still in the container. Let's assume that there's very little evaporation occurring at this point. So all the water molecules are staying inside the container. But I am changing the way the system's energy is arranged. Instead of at room temperature, all the molecules have a lower energetic arrangement. All right, if we think about energy as being a series of levels, right? Some of the water molecules will be arranged at lower energy, and some of the water molecules will have greater and greater energy, right? So I can, as I go up this ladder, I'm increasing the energy. So at room temperature, most of the water molecules are going to be on these lower rungs of my energy ladder. But as I heat the container up, more and more of the molecules are going to have higher and higher energy. So I'm changing the way the energy of the system is arranged. And if I change the way the energy of the system is arranged, I'm also changing its entropy. Another way to think about entropy comes back to this idea of equilibrium that you talked a lot about in sophomore year. As a system progresses towards equilibrium, what that system is doing is it's changing its arrangement. Now, the molecules might be changing their physical spatial arrangements, or they might be changing their energetic arrangement. But one way or another, as a system is moving towards equilibrium, it is changing its physical or energetic arrangement. And entropy really is a measure of the extent to which we have progressed towards equilibrium. To help you understand this maybe a little bit more, let's go back to kind of a simple thought experiment. Take a container of perfume, and we have the perfume covered. We know that all of the molecules of the perfume are inside that container. But if I take the top off of the perfume, we eventually, in a couple of seconds, we can begin to smell that perfume. What's happening there is the molecules of the perfume are beginning to disseminate or beginning to diffuse into the larger volume available to the room. It's beginning to change its spatial arrangement. When you open up the container, the molecules are going to sort of quote-unquote want to expand into the larger volume. That's how they're going to progress towards equilibrium, is by going into the larger volume of the room. So when we think about this thing called entropy, let's think about it in a couple of different ways. Let's think about it not as randomness or disorder, but let's think about it as how are we arranging the particles of the system? Are we physically moving the particles around in space? And or are we changing the energetic arrangement of the molecules that might be in the system? So think spatial arrangement and energy arrangement when you think about this thing called entropy.